Good afternoon, everyone, and welcome to another NERDIC webinar series. We have a full jam-packed 90-minute schedule with you. If you are one of our returning viewers, you'll notice that I am not Ron Angelo, who is the Connecticut Center for Advanced Technologies President and CEO. Instead, you have me, and I recently joined the CCAT team as their Chief Technology Officer, and I'm absolutely thrilled to be here today, especially as a woman in manufacturing and technology, to be a face in the midst of all of this technical ecosystem that we have as far as the New England Regional Defense Industry Collaborative. So today we have a really great featured speaker, which culminates on our four-part series focused on additive manufacturing. Today, I'll go through our agenda, which you see here. I mentioned that we have our focused on additive manufacturing. We started with generative design for additive a few weeks ago, and here we are today to talk about Powderbed Fusion and Bound Metal Deposition from the team at the Center for Additive Metals, University of Maine, their leadership there, as well as the Vermont Manufacturing Collaborative at Vermont Technical College. Excited to also have a graduate student, a part of that technical team from the University of Maine, to present. Our opening remarks will be featured by our NERDIC Steering Committee Chair, John Riandow, and as well, Eric Fogelman will be joining me as the Constep Senior Technology Solutions Consultant here based in Connecticut. I will be also closing with the demonstration pilot application. So for those of you who do tune in and see Nasir Manan, he is on the road currently with some other engagements on behalf of CCAT, so I will be coming back. And our colleague, Jeff Crandall, who is our manager of additive manufacturing here at CCAT, will be joining us for Q&A. So with that, I'll say some remarks about our Industry 4.0 readiness ecosystem. I had alluded to the fact that we've been focusing these last few series on additive manufacturing. We started this journey with NERDIC focused on the defense manufacturing ecosystem. And really that began in April with focus on augmented reality and artificial intelligence. Following the next couple final introductory workshops will be on model-based definition, so focusing on big data and on machine probing. So that will close out our introductory workshop programming. And then following on to that, we have technology demonstrations, a part of this holistic ecosystem. As you can see here with all of the counterparts that really are a part of this regional collaborative, it's focused on a multidisciplinary approach that supports our region's defense industry supply chain. It really is fostering our partnerships between academia and research, and we have some presenters here today, as well as the manufacturing extension partnerships, and I know we have several on the line as well. So really this holistic ecosystem that we've been working years to build, it has culminated in what we have for our webinar series, which if this is your first time joining us, thank you for being here, but I encourage you to also go back and revisit some of our on-demand workshops as well. So with that being said, I'll invite John and Eric on the line to join me so that way they could have some opening remarks for our afternoon's audience today. And John, we'll start with you, please, sir.
All right. Well, thank you, Jackie, for the introduction. And hello, everyone, and welcome to the New England Regional Defense Industry Collaboration, better known as NERDIC, and the Connecticut Center for Advanced Technology, CCAT Industry 4.0 Technology Ecosystem. As Jackie indicated, it's a dynamic series, and we're very, but before I get into that, I just want to talk a little bit about NERDIC. It consists of government and private sector representatives from the 6 New England states, partnered in a collaboration to strengthen our region's defense and industrial base through advocacy and programming for defense supply chain businesses. The NERDIC Industry 4.0 readiness ecosystem is all about collaborating with organizations that touch the region's defense industry and provide support services and programs for continuous training. I want to thank my colleagues on the NERDIC Steering Committee for their support and creativity in establishing this program, as well as the cybersecurity training program established last year And as established last year, working with the New England Manufacturing Extension Partnership, MEP Centers, as led by Constep. I want to thank Ron Angelo and again, Jackie, thank you very much, and their team for assembling and launching the Industry 4.0 technology workshops and demonstrations. With today's workshop on Powderbed Fusion and Bound Metal Deposition additive manufacturing processes, CCAT will provide more technology workshops and demonstrations through August of 2021. We are excited to continue the Industry 4.0 Technologies Ecosystem Program and hope you register for future sessions. Thank you.
Thanks, John. And some comments from Eric, please, from Constep.
All right, thank you, Jackie. Thanks everybody for joining us again. I'm happy to be here. Glad to be supporting this discussion. This is exciting stuff. Myself, I'm an engineer by background. And I've been in the manufacturing industry for more years than the color of my hair might suggest. But if you look carefully, I am starting to get some gray hair in my beard. So, this is exciting technology and it's exciting innovation. It's something that I've been watching for a number of years. Initially, additive manufacturing really started out, to be kind of pigeonholed into the rapid prototyping and custom fixtures. But now we're starting to see more applications for final production and production at scale becoming a reality. With the addition of new materials and combinations of materials, being able to process two different materials into one piece, it's opening up a lot of doors for, and a lot of opportunity for new innovations in this field. And then we're also seeing a lot of these new processes and post-processing methods that are opening up possibilities to add strength and structure to parts to allow them to go into application spaces where they weren't able to before. But more importantly, at least from my perspective, we're seeing the advances in the supporting technology that allow us to integrate this additive process into the digital thread of Industry 4.0, where we can feed model-based designs into an additive system for more seamless integration into that product life cycle. So I'm excited to hear about this today myself and add to that understanding and that knowledge of what's available and where the technology is going and how we can continue to innovate on it. So thank you. I appreciate the opportunity to be here.
Great, thank you for your remarks. And I think with that being said, I'll just cover some logistics about our afternoon's presentation. So there are handouts that are included in this deck as a PDF. So you have that as a reference as we go through the presentation. The question box will be open and available. So please do drop in your questions for the team as we go through their presentation. We will be addressing those at the end during our Q&A session. As well, if you don't already know, we have a very large following with all of these industry partners, the MEPs, on social media. So if you haven't already done so, I would encourage you to visit LinkedIn and go and certainly connect with our presenters this afternoon, as well as all of the partners across the NERDIC Industry 4.0 ecosystem. So with that being said, I will turn the program over to our technical team at the University of Maine, as well as the from Maine and Vermont. So John, I'll kick it over to you, sir.
Great, thanks, Jackie. Yeah, good morning or good afternoon, everybody. My name is John Belding. I am the director of the Advanced Manufacturing Center up here at the University of Maine. So we're going to go through a presentation today for you, talking about bound metal deposition and powder bed fusion additive metal processes. This is a great opportunity for us to do this. We really look forward to this, and the whole drive for our center and the University of Maine is to really help facilitate getting all of these technologies out to industry. And one way we do that is through these types of presentations. So I'll talk a little bit about the agenda today. And as we're going through the agenda, we're going to post a couple poll questions just to gauge the audience and see what status some of the audience may be in. And so for our agenda, we are going to talk about our Center for Additive Manufacturing of Metals, CAM. And then we're going to go over to the Vermont Manufacturing Collaborative. And Christopher Paulk will talk about their project and what they're working on. And then we'll talk about some value drivers for market and market size. And then we'll talk about the additive metal process, so a couple different additive metal processes that we're working on. And then we'll do a little bit of a deeper dive into bound metal deposition. We have a desktop metal system, which you probably heard a little bit about last week, and we've had one for almost 2 years now, and we'll talk about what we've learned and what we've been working on with our graduate student and some of the studies that we've been doing with the process. And then we'll wrap up with some additive metal case studies that we have worked on directly with industry. And so you can see the quick poll on the screen there, how many AM parts has your company made or purchased in the past year? So if you wanted to go ahead and answer that, and then we can move on to the next one. Yep. So, all right. Does your company design for additive metal? Yes or no on that one? And then again, we'll move on to the final question. Do you own any 3D printers? If yes, desktop polymer 3D printers, large scale polymer, or metal printers, or do not have one. So just trying to gauge, the audience here that we're talking to today, just to see where people are at. Great, and with that, we'll get into the presentation. We can go to the next slide. There we go. So I'll talk a little bit about our Center for Additive Manufacturing of Metals at the Advanced Manufacturing Center. So we currently, like I said, have a desktop metal studio system. We've just upgraded that system to System 2, which will remove the liquid debinding step of the process, but keep the thermal debinding process. And then we're also expanding our center into directed energy deposition as well. We are currently purchasing a Vitek 5-foot by 10-foot 5-axis 6 kilowatt laser, fiber laser, that will be doing directed energy deposition as well. That'll have a 4th axis and a 5-axis head, so we can do both flat planar type parts, but also more complex parts as well. And that will not have an atmosphere, so that'll be just non-reactive metals. Some of the software that we use in our center is SolidWorks. We also use PolyWorks for some of our metrology, and then we're also using AlphaStar and Simula for doing some model-based simulation as well. We also have a suite of QC and characterization equipment. We have a Keyence VHX 7000 topology microscope that has really allowed us to really look into microstructure and build up microstructure of the parts and pieces that we're making. We also have a ferro arm with the HD laser scanner, and we also have load frames and cross-sectioning capability. And we just also added in a large CMM with vision capability as well, so we can look at more parts and larger parts in detail. And then we have 34 industrial partners that signed on with us when we started our project from all over New England, but mostly Maine-based. And you can see some of the partners there on the list. And our goal is to really get this technology out to industry. And you see Pratt & Whitney on that list, and hopefully they're joining us here today, but they actually saw the benefit of this technology and decided to put that into their facility down in Berwick, and are now 3D printing with the system as well. So that's, a very good win for this project, is to get this information out. So go ahead, Brent. Additionally, for add-on, we've had additional $2.5 million in award from our original grant, and we won Innovator of the Year award from the Manufacturers Association of Maine. So really the CAM emissions and objective, and I've talked about this already, is to transition the additive metal technologies into industrial solutions and really show companies what it means to have one of these systems, what the cost drivers are, what the training requirements are. what they would need to put into place to be productive and to be able to utilize a system like this. And it's a fairly unique system. It was very new when we first got it, and we've learned a lot, and we'll learn a lot more about it today. Go ahead. So our CAM timeline and status, like I said, our grant was funded back in July of 2018. Our desktop metals machine was delivered in April of 2019. And since then, we've completed over 30 industry projects. We've worked on sustainable funding. We've really been able to extend the funding from this grant into many other grants. And we have an additional 1.5 million in pending grants for Industry 4.0 and AI work as well. So we're very excited about that, and hopefully we hear about that pretty soon. For applied research, we've had 2 conference proceedings and 3 conferences without proceedings. Thanks to Alex and Brett working on all of those. And then, well, we've done quite a bit of industrial and academic outreach, doing presentations like this. We've expanded into capstone projects. So we have students working on capstone projects with the equipment. We have over 200 engineering students that we train on additive every year. And then we've also been working with companies as well, so going out to companies, having companies come to our center and learn about the machines and equipment. And just a quick snapshot of some of the work that we've been doing. Been working quite a bit with Hussey Seating down in Berwick. They're one of Maine's oldest companies. They started out building plows, but now build stadium seating. So they build lots of different types of stadium seating, indoor, outdoor, and some of the bleachers that you pull out at a high school basketball game. But they have a lot of parts and components, and some of them they would like, want to test out before they have a casting mold made. And so we're able to actually build up 3D printed parts that then they can test within their systems and then go after a casting later on. Then you see some first robotic gears. Some students came to us and said, hey, we can't buy these off the shelf. Can you print some out for us? And then we also have some other systems where we've tested and pushed the limits a little bit, some plasma coating cells, some manifolds, some pressure manifolds. So looked at, pressure capabilities, and then had some students working on Stirling engines. And we'll show a video at the end. We've actually been successful at that. And then some other just unique parts that companies want to develop and test out. And a lot of companies will send us prints of obviously stuff that's been subtractive machined and previously, and then we work with them to help develop a as printable version where we can really optimize that design. And Brett and Alex will talk a little bit more about that later on today as well. Go ahead. Additional capabilities up at the University of Maine. Some of you may have heard about the world's largest 3D printer. So we have a polymer-based printer that is printing, as you can see in the video there, it's printing a full-scale boat, and we have our delegation and president of the university on that boat in our wave pool up here in Orono. And so it's a great technology, and really rolling that out for mold making, wind blade making, boat mold making. So really looking at much larger structures and how we can facilitate using a renewable resource, wood fibered plastics to actually manufacture those types of molds in large environments. Ben? Yeah, then I'll turn it over to Christopher Paulk from the Maine, from the Vermont Technical College, and he'll tell you a little bit about what they're up to in their process.
Yeah, thanks, John. Appreciate it. Good afternoon, everybody. My name is Christopher Paulk. I'm with the Vermont Manufacturing Collaborative. I'm currently serving as the executive director interim for Vermont Technical College, overseeing this project. The Vermont Manufacturing Collaborative was a joint project between higher education, the DoD, the Department of Defense, the Vermont MEP, which is VMEC, local industry partnerships, and our economic development offices. The idea behind it was to stand up an advanced manufacturing center focused in the Randolph Center campus, basically with an additive focus that would bring in about post-processing technologies and essentially trying to build bridges across the industrial skills gaps the DoD is seeing within their supply chains. So we'll have an initial focus on additive manufacturing. We'll basically put in all kinds of post-processing technologies in place to support that kind of technology. And the goals from this entire program is really to engage students in 3D basically printing platforms, all the skill sets that support that, from CNC machining, CAD/CAM, QA, QC, metrology. You guys can kind of read that there. And then also in looking at the developing and enhancing industry partnerships, internships, continuing education programs and opportunities that we can have, as well as trying to become a hub, if you will, within the New England region for all of our basically partnerships within universities, colleges, industry partnerships, where they can utilize the facilities with the curriculum and the expertise to really try to provide multiple pathways back to manufacturing. We really see this as a big partnership, and that's why it's been really important with you, Maine, and especially John Belding and Brett and Alex on the line today. And then as well as our partnerships throughout the New England region with our MEPs, because it's really a driving force for us to start to develop training metrics and platforms for our technicians that are coming through manufacturing, and also to try to kind of develop pathways back to manufacturing for our students and our workforce. And so with that, the new center will be completed September 1st, hopefully, is what we're looking at. We're on target right now for construction, which is everything's moving smoothly, thankfully. And in large part, too, really because of our partnerships with UMaine and others that kind of help drive us and steer us in the right direction when it comes to equipment selections. So a lot of this technology, as you guys are going to see today, as Brett follows up, after me, a lot of this technology is amazing. It's very complex. And for us, kind of being newbies in the region, having these regional partnerships is key, and especially with our partnerships with the MEP network is profound, and being able to have the interface with industry and what that looks like. And so, Brett, if you can move to the next slide for me real quick. Some of the equipment, guys, that's going into this place, we've already purchased an EOS M290 Powderbed Fusion machine, which is going to be kind of our big guy that we have in there, as well as a DMU 75 monoblock. This is a DMG Mori unit. It's a 5-axis CNC machining center. I call this my Ferrari. It is a big, beautiful 5-axis machining center that do all the post-processing for us as well. And next slide, please, Brett, if you don't mind. And then next thing that we've looked at, we've also purchased a smaller EOS M100 machine to get a little more throughput with it as far as training students and stuff like that, as well as we're doing a CT scanning. We've got all kinds of binder jet stuff we're looking at as well. A whole assortment of smaller polymer machines. A lot of metrology stuff, microscopes that are going in this place. So we'll basically essentially have a complete additive center, really accessible for the entire region to utilize, and especially in this partnership with NERDIC and CCAT and everybody else, it'll be a great opportunity for everybody to utilize, and a great platform to start training people on and to utilize it for any kind of technology development you guys would like to have. So with that, thank you for letting us have a little moment there to kind of chime in and show you what we're doing in Vermont. And with that, I'll turn it over to Brett.
Okay. Thank you, Chris. So next I want to talk about the value drivers and market size for additive manufacturing. Now, hopefully this is a review for many of us, but just kind of to see where we are. So some of the classic case examples include the GE LeapJet engine. This particular engine is quite exciting. The fuel nozzle, in which they took 20 parts and reduced it down to 1, and they were able to extend the life due to the ability to add conformal cooling. More examples include biomedical examples. There are industrial examples of additive manufacturing of metals. In this case, a 91% weight reduction at the end of a robotic arm, thus leading to faster cycle times. Quite exciting example, non-metal, but is in footwear. So can you tailor footwear to the application, such as a second baseman requires a far different kind of response on their feet than a pitcher might require. There's a very famous example of the nacelle hinges for the Airbus A320, in which we go from a kind of a welded type example in the back left and towards the front right, we get to topology optimized additive manufacturing type of shapes. An exciting example of additive metal is when we start looking at conformal cooling and the placement of cooling paths within the circuit. So here we have the exterior of the part, and the blue lines in the right image represent the cooling path. These cooling paths are feasible because of the additive, and you're able to place the cooling path wherever it's most needed. And as a last example, we can see mass customization. It's another advantage of additive. In this case, BMW, it's a BMW i8 Roadster part. BMW has built more than 1 million additive parts between 2010 and 2019. So looking at the examples, we start to see some sort of general framework of how additive can be used to come to a value for a customer. So on the vertical axis, we have unit manufacturing cost, and on the horizontal axis, we have part complexity. For very simple parts, as typically done with traditional manufacturing processes, oftentimes additive manufacturing is more expensive than traditional manufacturing. So additive is shown as the red line and traditional is this gray. If we start considering the process cost advantages of additive manufacturing, we get things such as shortened lead times, being able to go from maybe 12 weeks to get custom jigs and tooling ordered to maybe a week or two. We get these shortened lead times. We also get to what's known as the buy to fly ratio, in that many times in aerospace, you might buy a 100-kilogram billet and you're machining that down to it's maybe 5 or 10 kilograms. So a huge portion of the mass is removed from the billet. So that's this buy to fly ratio. And we also see the mass customization that was in the BMW example, or that we also find inside of biomedical applications. And lastly, when we look at some real value opportunities for additive, we get to the design advantages. In these, we have things like part consolidation. That's with the GE LeapJet engine, where we take from 20 parts down to 1 part for a 95% part consolidation. You have lightweighting. There's examples where brake rotor calipers are being built, and if we can reduce the amount of weight in cars, particularly race cars, etc., or aerospace, it becomes very valuable. And we also have these enhanced functionality, particularly conformal cooling is one of them, and another emerging application are heat transfer media for aerospace applications, places where we can enhance the heat transfer and reduce the weight. All of these become extremely attractive kind of applications for additive manufacturing, particularly of metals. So here's a snapshot of some value drivers by the application. You'll see that with prototypes, we see that we get performance and time advantages, and these kind of range. So clearly down here, we have conformal cooling, where we get a performance improvement. We get a reduction in lead time, but also we can get these into some sort of production kind of process. And there are some additive manufacturing of metal applications down here at the bottom where you can get to multi-metal, so like functionally graded metals, things that are just very difficult or impossible through traditional manufacturing processes. All of these advantages have led to a huge growth in additive manufacturing. In 2019, the additive manufacturing market was valued at $11.9 billion and growing at 21% per year, and serving markets in aerospace, defense, automotive, biomedical, dental, footwear. In particular, like dental is really adopted to additive manufacturing, and you see this tremendous growth since about 2009. This tremendous growth is projected to continue for years to come, and that we're seeing value growth with additive versus traditional manufacturing methods. So because of that, let's first take a look at what might be some of these additive manufacturing processes. In general, there are 7 types of additive manufacturing, and then there's an 8th type that's known as the other hybrid. Probably most people, if you have a residential type of a polymer extruder, as discussed in the poll question, you're very familiar with this material extrusion in the top left. Essentially, you heat up a solid, it goes through some sort of phase change, it liquefies, and then it resolidifies into some sort of solid object. We also have material jetting, in which you have a polymer, photosensitive polymer, which is laid down. Here you have a UV light which passes over the polymer, cures it, and forms a solid. There's binder jetting, in which you have a print media in a bed, typically like a powdered metal, a powdered ceramic kind of material. And then you lay down a binder, which then binds these together. And sometimes there's post-processing, which we'll see in some of the later slides. There's vat photopolymerization, in which you have a liquid photosensitive polymer, and then you pass a UV light over it. A powderbed fusion, in which you have a bed of powdered metal, and then you pass some sort of heat source over it, typically electromagnetic radiation, which causes the powder to liquefy and then resolidify into a solid. The next one is directed energy deposition, in which you have powder being fed down, and then the electrical energy or electromagnetic energy strikes the powder either mid-flight or right as about as it's placed, and so it liquefies mid-flight and becomes a solid upon solidifying at the surface. We can have sheet lamination, and then the last category is other hybrid, which we won't go too deeply into today, but it's quite an exciting field with friction stir welding and some other applications. If we look closer and kind of focus our search into types of metal or types of additive manufacturing of metals, we have subcategories here. So clearly the ones that are UV sensitive photopolymers kind of go away, they're grayed out, and the sheet lamination goes away. So we're left with material extrusion, binder jetting, powderbed fusion, directed energy deposition, and these other types. So now we're going to pass through each one of these, at least the first four, and kind of summarize what the technologies are. So with material extrusion, the basic process as shown in the video is we first extrude out typically a binary composite of the metal and a binder, and you also see some white here for interface that goes in between there. You'll then take the part out of the printer. It goes into some sort of debinding solution, typically organic solvent. That process typically takes 48 hours or so. Obviously, this video is a little bit of time lapse. And then it goes into a sintering process, and the sintering process elevates temperature somewhere around, well, it depends upon the material, but probably somewhere around 1350, 1400 degrees C. And we have solid metal parts that come out. So essentially, it's a three-step process consisting of extrusion, debinding, and sintering. Commercial equipment in this space includes the Desktop Metal Studio Plus system, the Studio 2 system. At University of Maine, we have the Studio Plus system, and it's being converted to a Studio 2 right now. And Mark Forge is also in this space with the Metal X. Characteristics, typically these types of machines, they'll deposit around 10 cubic centimeters per hour. Layer heights are about 50 to 220 micrometers. And you're printing a single material, and you require some sort of post-processing. We also end up with small thermal gradients, and that the fusion process is typically at a small thermal gradient, meaning the object is mostly at the same temperature. For those that have never seen sintering before, here's an SEM image. These two particles will sinter together. Kind of back it up maybe. You'll see here's a particle, there's a particle. And it's a solid state process, and you typically raise the temperature just below the melting temperature, and the particles will fuse together. It's the driving force is a minimization of free surface energy, and it's important that it's a low thermal gradient process and that you don't end up with a lot of thermal distortions, or at least less so. Our next type of process that we're going to look at is binder jetting. So in binder jetting, we have a debinding or a binding process where you have powder bed. So down here is our powder bed, and then it's going to lay on top a binder, which will then bind the powder together. It then goes through a debinding and a sintering process after that. So let's see what this looks like. So here is a cartoon of the process. You'll see there's powder going in through a recoating process. It goes on top of the previous layer. In this case, they're laying down two layers of grains, 2 layers of particles. And after those are laid down, next a print bed will go over, and it will spray down the binding agent, which will then solidify, at least temporarily solidify the particles together. And here comes the binding agent being laid down. And so this takes the particles, and if it attaches them together until the point that we can pass through a debinding agent and sintering, which actually forms the solid. Going to that same sintering mechanism we saw previously. Commercial equipment in the space, particularly X1, is quite dominant in this space with the InnoVent and the X1 25 Pro, Inflex, and X1 160 Pro. Importantly, you see very high deposition rates. If you recall the extrusion, it's about 10 cubic centimeters per hour. Here it is 100 up to 6,000 cubic centimeters an hour, and you can get much larger build volumes. Layer heights are typically on this, 30 to 200 microns, which is similar to the material extrusion. And we end up with things like single material printing. You do have to, you must have a hole in sort of any sort of solid shell to allow any particles to pass out of your object. That way, because if you bind the outside but have a bunch of powder on the inside, what you're going to end up doing is just fusing those together during the fusion process or the sintering process. But we can get to very high deposition rates, and so you start rivaling some of the, it addresses one of the primary concerns of additive, and that's the slow nature of the process. The next process we're going to look at is powderbed fusion. So in powderbed fusion, you have a powder bed, as you would imagine. Here comes the recoater passing over, and then some sort of electromagnetic source liquefies, and then liquefies the powder, which then cools and solidifies to become a solid. So here, that process is kind of sped up, and now we'll see a schematic of this, obviously at a much faster rate than what you typically find. So you have the part, and here's the actual how fast each layer takes. Each layer is about 30 to 100 microns. So here the part is being removed from the powder bed, at which point you can do any sort of post-processing. Here they're taking off the thermal boundary to allow heat to escape, any sort of cleaning the finish, and post-processing. So commercial players in the space include EOS, such as it's taking place over in Vermont. There's Readiness, there's the 3D Systems, and also Arcam. Build volumes are, they're on the order of what you'd find in material extrusion, maybe not quite as big as the binder jetting. Layer heights are relatively fine. One important thing with this process is that you get large thermal gradients. So as you have a solid at the lower levels, you place a powder, and then I liquefy and then solidify on top as it cools. And that leads to very large thermal gradients, which can lead to residual stresses and texturing. What I want to look at next is a SEM image that shows this process of solidification. So what we have is a powder bed shown here with all the powder. As the electromagnetic source passes over, what occurs is you get solidification. And you'll notice that what appears to be at the macro scale pretty much here's a solid taking place. You get things like, I'll pause it right there. You can end up having some pores that form. So here we have this dark black is a solid, this circle black here is a solid, but then we have space between, which is a void or some sort of pore structure that's forming. And so that's an important consideration with powder bed fusion. The other thing you need to consider with powder bed fusion is that you typically need an inert environment. Powder has a lot of surface to area ratio or surface to volume ratio, and you can have, it can be reactive in nature and lead to explosions. Typically, you have to convert or do powder bed fusion in some sort of inert environment takes place within the machine itself. And a last consideration, because of the large thermal gradients, that you can end up with what's different types of grains within the metal, similar to what you would find in casting. And so up here, what I have shown is on the vertical axis is a thermal gradient, or the log of the thermal gradient. So as you get a higher gradient, it goes up. A lower gradient is on the down on the vertical axis. Then we have on the horizontal axis is our solidification velocity. Very slow solidification happens on the left and very fast on the right. So what does this mean? Up here in the purple region, what we end up with is that this high thermal gradient, slow solidification velocity, you get what's known as columnar grains. And here is a image of these grains. So you can see these grains, each color represents a different grain, and you can kind of get to these very long, slender columns. And down in the red region, which is the equiax region, you get to this more preferred grain texture in which they're almost more circular in shape. So the key important thing here is that process can control how these textures are formed, and columnar grains can struggle in higher order mechanical effects like fatigue. So if you're making aerospace aircraft structures, what you probably want to avoid these columnar grains up here, and you want to be more focused in trying to produce these equiax grains on the lower right. The last process we'll look at is directed energy deposition. What you'll see is there's powder coming down right through here. When the powder gets to the bottom, there'll be a light that comes down, strikes the powder almost mid-flight, and it will heat the powder as it's traveling and liquefy the powder mid-flight. The liquid will then land on the solid surface and cool, thus forming a solid. And so it's almost like, it's a little bit like really fine welding. Players in this space include Optimex, Tiaki, and Beam. You generally get some fairly large deposition rates, about 15 to 130 cubic centimeters per hour. Build volumes can be quite large. Some of these can actually be outside of machines where you don't have a controlled environment, thus allowing you to do repair type of activities, which is quite exciting. Another cool and exciting parts of directed energy deposition is that we can get to functionally graded materials, meaning that we can transition from, let's say, like an iron to something else if you need to change the materials along the way, change the type of material along the way. These can be done in atmospheric or in inert atmosphere kind of environment. They're exciting because we can use these type of technologies for repairs. And you also get to this subtractive additive hybrid machining. So many times if you start off with a blank that's pretty large, add a little bit there and then maybe do some cleanup with subtractive, it offers an even more efficient use of additive and subtractive manufacturing. The last thing is substantially faster than powderbed fusion. If we look at a comparison of these processes, the things that I want to draw your mind to are right here. So we got the thermal gradients. Material extrusion and binder jetting typically have very small thermal gradients. So you're going to have a large amount of, well, we'll discuss about shrinkage later, but typically you end up with less texture problems. So less columnar grains, more equiax grains. Over here with powderbed fusion and directed energy deposition, it's very possible to end up with grain textures that are maybe less desirable. The other thing I'll kind of call your attention to is this relative cost. So material extrusion is really one of the least expensive ways to get into additive manufacturing of metals. Powderbed fusion is typically more expensive. You can get finer control. Powderbed fusion is more common in aerospace and biomedical. And as additive manufacturing metal gets more closely aligned with, I'll say, traditional industrial processes, you're going to find that material extrusion and as high volume, probably binder jetting are probably going to be more dominant type of roles, with directed energy deposition definitely playing a role with enhanced functionality and anything to do with repairs. So let's take a deeper dive look at bound metal deposition. This is the type of system that we have been running at the University of Maine for a little bit over 2 years now. So bound metal deposition includes these 6 steps. We start off with digital design of the part, goes to slicing, we then print the part, goes through a debinding process through an organic solvent, sintering in which the metal is fused together, and then any post-processing that needs to take place. So after the digital design has been done, we next go into the slicing, and with slicing, here is an image from Desktop Metal Fabricate, and this happens to be from a Stirling engine from a prior year. And so these different colors have different representations. So starting in the middle, what we have is infill. So just like the material extrusion machines that you have at the residential type level, like an Ultimaker or a MakerBot or some of those type of machines, we end up with infill. The Desktop Metal happens to use a triangular infill, and you can control the density and spacing of the infill. And it also places most of the metal out the outside. So you get an outer skin shown in gray. You get inner walls, and those are selectable, shown here in orange. In this case, there's a total of 3 outer layers. So we have the outer wall with 1 layer and 2 inner walls shown right here. So a total of 3 layers right at the outside, or 3 walls right at the outside edge. And the infill comprises a hollow with a infilled center section. At the bottom, these parts are built upon a raft. So here the raft is in the slicing shown as blue. There's a ceramic interface that separates the raft from the desired part for the sintering process. Otherwise, the raft would sinter to the desired part. And so this shows the ceramic interface as purple between the outer wall of the part in gray and the ceramic interface in purple. If we look at printing, you'll recognize this if you have a residential scale polymer machine. It's a very similar process. Essentially, you start off with a rod of the material from the manufacturer, and it goes through almost what you'd imagine as a hot glue gun. So it's heated and forced through an extrusion nozzle, in this case a 400 micron nozzle, and through the G-code it prints the part. Currently today, these materials can include a 316L, a 17.4 pH, a 4140, an H13, and copper. All of those are commercially available. There's a nickel-based superalloy that's being developed, as well as other materials that are in development. If we look at that extruded filament through an SEM over here, so this is the entire extruded filament. This thing across in diameter is 400 microns, roughly. So the black regions represent what the binder looks like, and these white regions are the metal powder. And so here we can see this metal powder is mostly spherical, and it's on the exterior. It's also all the way through. It's just that with the SEM, you don't see the interior of the extruded filament. Once the part is printed, it then goes to an initial debinding process, typically an organic solvent. This debinding process depends, the time it takes for the debinding process depends upon how thick the sidewalls are. So for something that has this three wall layer, maybe like an outer wall and two inner walls, it's going to take less time than something that has maybe 6 walls or 10 walls. There are maximum thicknesses that we can run the walls. But the debinding time just depends upon how thick those walls are, and you can batch these jobs together. So you typically print 3, 4, 5 parts, and then you take them, put in the debinder, run them as a batch for 30 to 40 hours, and then they're ready for the sintering process. If we look at a part after it's been debound, what we'll see is we have everywhere where there's black, it's this polymer that we're seeing, and all these white spheres are the metal powder. So you see that there's quite a range in powder size, some relatively large like up here, and then lots of relatively small kind of powder sizes. This powder size is different than what you're going to find in powderbed fusion. One of the reasons why material extrusion is substantially less expensive than a powderbed fusion is that with powderbed fusion, you have to have very consistent size particles. And that's to make sure that you don't get vaporation or ablation or any other type of deleterious process during as heat goes into each particle. But here, because the thermal gradients are low, you can use more of a developed powder stream. Typically for metal injection molding is where that powder is coming from. Very similar process. Then we also see some sort of fibrous type of structure here that kind of holds it together. So in this state, they're fairly fragile. You don't want to be shipping the parts around. Typically, you kind of want to hold them at one facility. I mean, you can hold them, but if you squeeze them or if you press with your fingernail, you'll actually damage the part with your fingernail just pressing in. So they are somewhat fragile at this point. After they come out of the debinder, they go into a sintering step. So here is an SEM. After you heat up to about 150 to 200 degrees C, depending upon the binder, what happens is the binder will evaporate and you're left with just metal particles. So here's the metal particles right here. As we continue to heat up to around 1350 or so, what will happen is the sintering process will take place. So here we have those particles and they'll fuse together in the solid state sintering. And whenever it's done, what we end up with is a microstructure on the far right. And we'll look at that some more in the next slide to come. So a couple of characteristics. So we have a max temperature, the sintering temperature is somewhere around 1350 to 1390 degrees C for a 17.4 pH, so right below the melting point. Sintering gas, it is an inert environment. So with argon, there's a little bit of hydrogen to remove any oxygen that happens to be on our particles. It's at 100 torr pressure. Typically, it takes about 36 to 48 hours, and you do get some relatively large shrinkage, as you might imagine. So here we start off with powder, and you see there's lots of voids in this powder, and whoops, and it's going to center down to right here, and so you get shrinkage on the neighborhood of about 18 to 20% shrinkage, and it's a little bit directional dependent also. That shrinkage is handled within the software, so all we have to do is provide, here's the final shape that we want, and the software is smart enough to apply the shrinkages as need be. If we look at the as centered right at the interface, so this is where we have the ceramic interface that separates the raft from the as desired part. Well, we can see there's these little ceramic spheres, and these spheres are what prevent the raft from centering together or fusing together with the part. Kind of interesting. And now just a generic summary of where the system capabilities are. So in the as-centered state, the Desktop Metal Studio Plus system can produce a 24 by 16 by 16 cubic centimeter part. We have a maximum of 10 layers for the wall thickness. The morphologies, there's infilled with closed microstructures are most common. And its depositing or deposition rate is somewhere around 10 cubic centimeters per hour for the as-centered state. If we look at some of the characteristics of the as-centered part, so here we happen to see the surface roughness. On the top surface, it's going to be a little bit smoother than the bottom surface. The bottom surface is intentionally a little bit coarse, a little bit rough, and that's to help with separating the raft from the part. Now, this slide or this image is a little bit old. There's since been just recently an update to the software where it's not quite as rough as shown here. So on the top surface, we have roughly 30 microns from peak to valley. On the bottom surface, it was about 270 microns. If I had to guess today, it's probably maybe 170 microns from peak to valley. There is a finer diameter nozzle that's 250 microns that you can actually get a smoother surface finish if desired. There's also, you can do post-processing, so a little bit of treatment in that either as printed or as debound state, and you can do some cleanup on the surfaces. For those, well, this type of process is a near net shape process. And so to kind of check out how near net shape happens to be, here is a digital design part, printed off 2 of these parts to get a physical realization and scan those parts. And what we see over here, compare the as realized to the as designed. What we see is that in general, we get typical conformance of about 50 microns or about 2,007 inch. Now for this thin overhang, it's kind of a tough part, and there's an interface on the bottom, there's an interface on the top, and so it's going to want to sag more. There it was a plus or minus 350 microns or about 14,007 inch. And so it's fairly close, but it is a near net shape process. If we look at the microstructure, so here is a tensile coupon for some tensile specimens we ran. This is the cross section. We take a close-up look at that one particular cross section. We see all these types of voids, and so we end up with these inter-raster pores. That is a pore that occurred between 2 rasters, and then we get intra-raster pores, and that's just due to the shrinkage and the ability to take these particles and form them to a solid. You get a little bit of pore that remains. At the bottom, we just see the bottom, and this is how the surface roughness looks on the bottom for the prior generation of the fabric or the slicer. If we zoom into just the section, we can look at things like analyze the microstructure and see that in this particular section, it's about a 2.7% porosity. Mean pore radii is about 6 microns with intra-raster pore somewhere less than 10 microns. And over here is the frequency of that distribution. As mechanical engineers, we're probably more used to these mechanical properties. So here we have stress strain curves for the as-centered 17.4 pH, and just for reference down here is PLA. So we end up with stiffnesses and yield strengths and tensile strengths as shown on the right. And probably almost even more importantly is this next slide, where we start comparing what we get with bound metal deposition versus what you see with wrought or as-centered metal injection molding for similar materials. So we get a modulus of elasticity of about 180 GPa. That's a little bit less than what you'd find in a wrought material. Yield strength of 600, once again, a little bit less and a yield strength of about 800, 775, which is also a little bit less. Elongation is a little bit less. Hardness is, once again, a little bit less, and porosity, there's a little bit of porosity there. So it's certainly comparable, certainly allows you to do new things with additive manufacturing of metals that you'd hope to do. It doesn't quite get you all the way to rot. However, I'll also comment that rot, you have some wasted material, right? There's portions of the geometry that are not very utilized. They're almost like lazy material. And so because of that, it's a higher utilization of the material that is placed, although there's a small derating of the materials as you're going through and looking at mechanical properties. So what I want to do now is turn it over to John, who's going to speak to additive manufacturing of metals case studies. So John.
Great, thanks, Brett. Thanks for all the info. Yeah, so we'll, yeah, this is a unique one. This is not a case study that we did ourselves. This was one that was done in GE in collaboration with GrabCAD. And they threw it out to the world to say, okay, who can basically generative design a better bracket than what we did subtractively. And they were able to take this in 2013 and basically take over 3.3 pounds of material out of this bracket, which that equates to over $200,000 to $300,000 per year per carrier, and up to $9.5 million for all commercial aircraft. So one small change on a piece of aircraft is a huge benefit to the industry. And looking at the design, they basically threw it out and said, okay, what's the challenge? We had, I think they had, you can go to the next slide, Brett, over 700 entries and from about 320 different designers. And like I said, the winning design reduced down to 0.327 kilograms per bracket, and that's about 0.7 pounds. So it took a lot of weight out of that bracket. And you can see in the design, the winning design, how they managed to basically carry the loads throughout that structure, and the generative design that they did use to do that. If you look down in the notes section down at the bottom, there's some PDF slides there that go into more depth into this model and talk a little bit about the loading and how they loaded it. They gave a very specific load pattern and what they needed and how to, what they needed for design parameters, and then let designers come forward with designs. And so pretty unique way to do it. It allowed it to, take place all over the world, not just one locality. And I think they said they had basically over 700 person hours of design work that went into it. So go ahead to next step. This is a project that we did, and we work very closely with our main MEP center. I didn't mention that before, but this was an MEP project that we did with a local bakery here, and this is Labreeze Bakery. They are a company that makes a lot of cupcakes, and this is a gearbox that drives the frosting mechanism that puts frosting on large plates of cupcakes. And unfortunately, the gear in that gearbox failed, and they contacted their supplier and said, all right, we need a gear. And their supplier said, well, unfortunately, COVID's going on, and it's going to be 3 to 4 months before we can get that gear to you. And so they came to us and said, hey, is there any way we can recreate this and get us back up and running? And so we said, well, we'll give it a shot. And luckily, this is a very low RPM process. It's not a high-speed gearbox. It basically does an oscillation. There's a servo motor that, there's no shock loading really in it at all. And the servo motor that drives it forward and backwards. It doesn't move that many RPM per day. And it's a decent application for this. So we printed, as you can see, the top one is the damaged original gear. The second one down is as debound. So that was printed, then debound. And then the third picture down is the part as just before we put it back into the gearbox. We did a machining operation. We added extra layers to both the front, the tail, and the front shaft on the gear itself. Which gave us added material that we could remove. We put this part between centers to make sure that it was going to be concentric when we turned the ends off. And so turned those down to the specifications that they needed for the original part. This part is shrunk fit into that small gear that it's attached to, and then press fit into the bearing housing. That all gets slid back into the gearbox, and then there's another large gear that interfaces with the gear. On the involutes themselves, we just basically wire wheeled those. We knew the other gear was quite a bit harder, and so we figured they would wear in as it rotated. And we were hoping, we hope that they will be able to get at least, 3 to 4 months out of this gear. And as of right now, it's still running strong within their application. So, good. This is another great project that we're working on with a local company here in Bangor, Maine, called Intention, and they basically made trade show booths for the trade show industry. And now everybody knows what happened during COVID with trade shows, that just completely evaporated. So they really transitioned to making face mask materials and solving other problems using specialty fabrics. Hospital, they were already making face masks for hospitals, and the hospital came to them with a challenge. A lot of their doctors are using these half-face respirators that you see there on the right. They're using those in surgery and in critical areas within the hospital. But one problem with those half-face respirators is they have an exhalation valve on the front, so the air can freely exit the mask and it's not filtered. It's no problem for the wearer because they're getting filtered air coming through the filters, but anybody else in the room, it could be a problem if the wearer has COVID. And so we worked with them to help design a mold, an injection mold, that they have a smaller tabletop injection molding machine that's perfect for this application. And we just worked with them to design and 3D print, metal 3D print these injection molds. We tried doing some initially out of plastic just to kind of get the design right. The plastic ones only lasted about 10 to 15 parts before they broke. With the metal 3D printed molds, they're still running, and they've produced thousands of parts off them at this point. And it's not something they'll do long term, but now that COVID is kind of waning, they'll end up stopping the production on this. But another very unique process and a great challenge. And like I said before, we have a lot of students directly working on these projects too within our center, both undergraduate and graduate students. And we'll head to the next slide. And with that, I will turn it over to Alex, our graduate student here at the University of Maine within CAM, and he can talk a little bit more about some of the student-based projects we're working on.
All right. Thank you, John. Yeah, so this project on this slide that we're looking at was designed by MET students here at UMaine for a capstone project. And the scope of that project was to develop and manufacture a Stirling engine primarily using the BMD technology to kind of show off what it's capable of doing. So this project was 12 total parts that were manufactured using BMD. The total amount of printed material was of that 2.28 kilograms approximately. So that it is about 99.5% metal, and then a very small amount of interface material printed, as we talked about before, what that interface does. And then the final mass of those parts is the part mass once the process is finished. They're in the as-sintered state, so the binder material has been removed, and the wrapped and the interface materials are also removed from that. So to create these parts, the manufacturing time, that's the amount of time for the printer, the debinder, and the furnace to run and produce these parts, was approximately 170 hours. But the actual labor on the operator side, that operator was myself, was approximately 1 hour. That was just simple tasks like setting up the slicing through Fabricate, which is the desktop metal slicer that Bound Metal Deposition uses, and this unloading and loading the parts into the next machine as you go through the process, moving through that process. After they were sintered, they were then post-processed using some pretty common subtractive techniques. So there were some of these parts were turned and just polished up to meet tolerances that were necessary for the Stirling engine to run. And that took about 4 hours from the people who were doing that labor. So we can go ahead to the next slide. So here we're showing a couple of different iterations of the base part of this engine. So on the left, this is the initial base design that cracked. This came from the MET team in 2020. They designed this part, and then the part experienced this failure. It cracked right in half. Not ideal. So it was redesigned. Just some tweaks that were made in CAD, and then it was reprinted again in the next iteration of that design. And that final base design survived after some informed revision. So this one thing to highlight here is that there is no need for additional tooling or anything to produce this new part. All it took was some tweaks in the CAD design, and then you printed it the exact same process as printing the first one. So very quick, very easy iterative design with additive manufacturing. You can go ahead to the next slide. And here is a video showing that engine actually working once it was fully assembled. The majority of these parts were bound metal deposition, but some of the parts were, just there's some extra hardware and some cylinders that were taken from a Stirling engine kit. But yeah, it worked pretty well. Okay. Now back to John.
Great, thank you to the team for your very informative and in-depth overview of the various capabilities and going into more technical depth for some additive. As an electron microscopist myself, I was taken aback to some of the data, and one of my questions that I had dropped in the chat, and I'd invite Jeff Crandall, my colleague from our CCAT Advanced Technology Center, if he wants to pop in as our additive guru, but perhaps many of you will be able to handle questions. But when I was doing additive manufacturing on, in powder bed and directed energy systems, we were finding those columnar grains. And so I was enlightened today by learning about this point-based method to really achieve more equiaxed grains. So Dr. Ellis, I don't know if this should be directed to you, but I'm wondering what that, how much more time is it if you're dwelling the beam or the source on, on your metal versus if you were just to use a scanning approach. So I don't know if I would love to hear that answer if any of you could enlighten me.
Yeah, so that work came out of Oak Ridge National Labs. One of our collaborators out of the 34 industrial collaborators at Oak Ridge National Labs. They developed that. It's called the Dayhoff fill, and it has very similar characteristics to what you find in casting. So anytime you cast, what you have is you have the columnar grains on the outside down to the equiaxed in the middle, and similar type of behavior happens in additive. There's some really nice work out of Oak Ridge that they can actually, they use, it's hilarious, they use Powderbed Fusion as a typewriter, and you can actually type words by the grain texture. So they'll put, the letters in equiaxed and the surrounding letters in columnar. It's
very cool.
Fascinating. Yeah, a lot of fun stuff.
I'll have to check that out. As a former grad student myself, Alex, I want to direct this question to you because I was a materials engineer at UConn, and the ultimate question, right, is where are you going after you finish your degree? Are you going to go into industry, or are you going to stay in academia? So I don't know how long of a tenure you still have at the University of Maine, but I'm curious as to what your thoughts are of what comes next for you.
Sure. At this point, I'm very open to opportunities. I'm still facing at least another year hopefully out of here in a year, finishing up the research, at least my leg of the research, my contribution to it. And then after that, yeah, I couldn't tell you where exactly I'm going, and I think that's kind of a good thing. It leaves my options open, and I'm just interested to learn.
And I think with the trajectory in the market where additive is going, and certainly being a mechanical engineer and being so well versed in this really dynamic industry, you'll be certainly set. But I'd like to pivot onto the point of, we've seen a Deloitte study that has come out that has indicated that by 2030, I believe, we'll be having a manufacturing skills gap of on the order of over 2 million jobs. And so with both Maine and Vermont really targeting engineering students and working in collaboration with industry and other research organizations, I'm wondering what, certainly what we've heard is that there's a lot of training of engineering talent, a lot of internships that are, being started up and or continuing. So I'm just wondering where you all see the path. So I've asked Alex the question, he's kind of just like, we'll wait and see, I still have a bit of a runway left. But for those students that you are training up, I'm wondering if they're heading into the workforce immediately. Are they going into graduate school? Like, where is their paths, and how best can this Nerdic ecosystem really support them? So John, I'll have you answer that one first. And then also Chris, with your center coming up online in September, I'd love to be able to hear more about that as well. And then if you saw in the chat, I did target a question to you, so we'll come back to that. So John, if you wouldn't mind just sharing some thoughts.
Yeah, absolutely. Thanks. We have actually this year, it's pretty exciting for us. We actually have a high school student that's going to be coming in starting June 1st. It's going to be working through us with CAM over the summer. And then we also have undergraduates that are working in CAM as well. And we see those students as kind of just to start stepping stone. A lot of the students that come through our center, most of them are hired before they're even graduating at this point. And which is a great opportunity for those students. For example, Intention here in town, they hired 2 of our students before they even graduated. They hired them out in early January because they knew if they put the money on the line at that point, they could lock them in and get them at that point. So we see that as a huge challenge right now with the university and in STEM education. The University of Maine is currently building a 100,000 square foot new training center, engineering design center here at the University of Maine, which will have a lot more additive, but I have also a lot of capstone space and a lot of other spaces for doing more advanced manufacturing type work for those students as well. And we're trying to push more students through our program too. As we're a small staff, it's a little bit more difficult, but anytime we can get students experiential learning and hands-on and working directly with industry in Maine and New England is a huge benefit for everybody. So.
Yeah, and to piggyback on that, Jackie, that's a great question. Vermont Tech, what we're trying to do is we're kind of positioned uniquely in a very remote area, and to John's point, what we're trying to do is we have a stackable credentialing system in place, right? And so Vermont Tech boasts a 99% job placement rate out of their manufacturing program and MET program, which is exceptional. And at the same time, we've structured this program in a way where you can come in at any kind of level, be it a certificate, an associate's degree, and a bachelor's degree. We don't offer graduate studies. So that's kind of where these partnerships with UMaine and University of Vermont really kind of play a pivotal role. And if we have students that come through and want to advance their studies into those areas, we have avenues and relationships in place that we could basically bridge those gaps and put students into those pipelines. But in the meantime, what's nice about Vermont Tech is we're really kind of focused on the technology. We're focused on technicians and trying to bridge those industrial skills gaps. Like to your point, the Deloitte study, the DoD's seeing the same thing, right? We're seeing a huge, massive gap right now in industrial skills, and especially people wanting to get into manufacturing, and especially on the technician level as well, right? And so we're trying to use the additive world to really kind of be like, we call it our lighthouse effect, right? It's really where we're trying to kind of have that beacon where people kind of come back to manufacturing, they get excited about it again. And you kind of bring in our new generation, right, of engineers and manufacturing students that kind of want to do, they love the 3D printing world. They love, what that looks like, what it is, the design side of it, and then kind of trying to build back all that post-processing, skill sets and stuff to it as well. And so, yeah, so like we kind of give Alex a hard time because we're trying to steal him right now, and then come over and help us too, so on our side as soon as he graduates. So having good students like Alex is paramount, you know what I mean? And it's a great thing. So.
Yeah, it's certainly not a bad problem to have folks fighting over you, and hopefully there's a multiplicity factor there with all of the training and upskilling and access and opportunities that's available to students all across New England through the organizations that we're hearing from today, and also broadly across the Nerdic ecosystem. And so I know that I called upon Jeff Crandall, and I've stolen the show here. So Jeff, I don't know if you have any specific questions or thoughts of what you've heard from this team here on a more technical level.
Sure. We have some questions that have come in, so I'll go ahead and field those questions. So first of all, thank you guys very much. It was a very informative session and a lot of great information. So getting to the questions, what design codes and standards allow the use of additive manufacturing materials and methods?
Handle that one, Brett.
Sure. So ASTM is developing standards for materials and processes. One of the big challenges that everyone's working on is how do you know you've made a good part? That's still definitely an emerging challenge, and that's taking place. Oak Ridge is doing a lot of work with trying to do artificial intelligence and scanning of parts, trying to detect cracks in situ. But the challenge is that it's gone from you've had continuous manufacturing of materials to now it is batch manufacturing of solids. And, that's part of the challenge, right? Design and quality are the two of the biggest challenges out there.
Yep.
Good questions.
And on the FDA side, it's obviously, there's a lot of 3D printed implants and stuff now as well, which those are all handled by FDA and the traditional type of approvals on the FDA side.
Okay. Next question revolves around binder jetting. So here again, whoever wants to try to go ahead and handle this. So they're asking about, can you talk about the orifice size capabilities with binder jetting?
Ooh, off the top of my head, I don't know what they are. It's pretty fine. You can get some fairly fine orifices. We've had multiple material jetting as part of University of Maine for years. John has one currently there. We've had sister machines, one in my lab, one over at AMC. So you can get some fairly fine orifices that you can print off. But I guess long term, I think binder jetting is a very exciting technology. There's some cost structure advantages. There's deposition rate advantages. And I think one of the exciting parts about material extrusion is that it allows us to start working in that binder jetting light kind of technology and preparing for binder jetting in a more commercial fashion.
Okay. In regards to binder jet and Powderbed Fusion, those are probably the two most advanced manufacturing tools. Why would you choose one over the other? What are the pluses, minus, the qualities of one versus the other?
Yeah, I can
speak to that, John.
Sure. Yeah, and I think it really comes down to material deposition rate and cost. And so, as binder jetting is fairly new to the realm, I think it's definitely moving up in the ladder as far as what the possibilities are with the technology. The downfall to both is you can't tailor the inside of the material and do lattice work and things like that, but it's very good with solid parts that are fast, that you need a large volume of the same thing or different things even. But like with Powderbed, and with Fusion, you're making one part, you can maybe make a couple parts on your build tray. But the bound part, you can make a whole chamber full of parts for the binder jetting, which allows you to sinter all of those parts at once, so you can do a larger volume and much quicker.
Okay, so more serial production related with binder jetting. Yep. Okay.
Volume manufacturer. Yep.
All right, so a follow-on question to the earlier one just popped up. So about the design codes again. So are there design codes and standards that allow the use of the ASTM standards? So, you know, how are the standards being interpreted and applied in the design codes and you know, designed for additive? Or are they yet?
In general, I'd say it's emerging. What I would ask whoever asked the question if they want to contact us individually. So you're probably getting down to application specific or industry specific questions.
Mm-hmm.
And to start answering some of those, you know, if it's automotive or aerospace, it's going to vary. And so I think what we'd want to do is probably take a deeper dive and try to figure out what that is.
Okay. And just to talk briefly about standards as well, I mean, you know, here again, ASTM, ISO are, you know, coming out with standards as well as other industry standards organizations. Key here is that they're just an adjunct or an add-on to your existing quality system. So, you know, if you're involved in manufacturing, you have a quality system, and you know, you're going to have to explore what your end-use customer is going to ask of you, and what your industry is going to ask of you, and what the applicable standards are for that particular application and industry.
Yep. And I think, you know, the two big challenges I think for additive manufacturing are going to be design and quality, right? Because when we deal with additive, so previously, you know, with subtractive manufacturing, traditional manufacturing, the quality of the material is built into what the manufacturer buys, right? So you buy a billet and the billet's the billet, you've got material certs and off you go. Here you have certs for the raw material, but then it's so process dependent. You know, perhaps so for things that we've seen, looking at warpage of parts, we're currently looking at a warpage study. And so you change the orientation of the print, or you change left side to right side in the sintering oven, and it can depend. And so trying to go through and figure out what those dependencies are, because really it's now process, heat transfer, material science, mechanics, all of that's wrapped up into one. So design and knowledge are super critical now.
Yeah, you know, and that part that Alex showed with the Stirling engine of the one that's broken in half and the one that survived, I mean, there was a very small amount of changes between those two parts. Yeah. So it's, you know, and to getting those right the first time is the first through input, you know, is really what we've been concentrating on, is how do you get that first off part right out of the box, because that's all cost.
Okay, I think we probably have time for one more question before we finish up the session. So out of curiosity on my end is that what are each of you seeing in your area and your state, you know, in the region as far as adoption of additive goes? So who's adopting it? What are they doing with it now? And, you know, where do you see the future of the industry going?
Yeah, I can start, I guess. Yeah, so we're seeing, you know, a lot of different industries. Some is fixing a problem, like, you know, what we see with the Labreeze, where you're just doing a repair part. We've seen a lot, and what we've kind of tended to focus on is the tooling and fixturing side, which I think is a great opportunity. You know, there's examples of companies out there that, you know, they have their own plastic 3D printer, and they are able to print that, you know, plastic part or plastic tool first. They go down on the floor, they test it. Yes, it works great, but now we need to, you know, have that subtractive machined, and it can take, you know, 2 to 3 weeks to get that back from a machine shop, when you could just skip that whole process and print right to metal to begin with. Take it down on the floor. Maybe you need to do a little post-processing to it or machining on it to make it work exactly right, but you're ready to go right out of the gate. And we see that as a big benefit, and a lot of companies are starting to see that as well as a good way to bridge the gap, begin the technology, and then start to use it within their facilities.
Excellent. Chris, Brett, any?
Yeah, Brett, you want to go ahead, man?
Sure. I guess so. John is much closer with industrial clients than I am, but I would say that a lot of companies are additive curious, and their additive curious point taking, here's a subtractive part and can I make it additively? And I think the real question is, don't think about the geometry of the part, but think about the function of the part. What function do I need? And then let's figure out how to make that additively, because many times that's where the big cost savings come. And you know, when you start adding in functionality, conformal cooling, or these heat exchangers that are coming online, that's going to be where the real advantage is, not just taking, here's a subtractive part and making it through an additive process. That's great and leads to faster lead times, but we're not really leveraging the technology yet.
Yep.
Yeah, Jeff, like, you know, for the Vermont side of the house, yeah, to Jeff's point, right, a lot of curiosity out there. With us being tied to a DoD contract, obviously there's a lot of defense and, you know, interest. We're kind of aligning ourselves to that, but at the same time, like I've always, you know, I've got involved with Vermont last year, and I actually work as an advisor also with the Vermont MEP, and as I've learned, you know, Vermont's kind of a manufacturing boutique, if you will. You know, it's got such an assortment of different types, and I mean, we've even been talking like everything from, you know, aerospace to soap manufacturers. You know what I mean? So like for mold development, stuff like that. So the idea really is to kind of develop, you know, for us at least, a facility and a place where people can come in and do prototype development, do technology development as a resource to the MEP and to the regional MEP networks, as well as the universities. And so that we can basically kind of create project-based learning environments for our students, so they can be working on real-world projects at the same time. We can develop, you know, the understanding of additive throughout the region, and especially throughout the state. And that's kind of what we're seeing so far.
All right. Well, thank you very much. I'm going to turn it back over to Jackie, but appreciate that. It was excellent once again.
Thanks,
Thank you,
Jeff.
All right,
And
bye.
thank you all for being here today and to talking to us about each of your respective capabilities and Powderbed Fusion and all of the other additive manufacturing platforms. So thank you so much for being here and your time. And I will also just put in a plug, right? We want to also be connected via social media. So please find these gentlemen and their respective organizations and the Nerdic ecosystem. There's a plethora of networking that can be done. And on that point, we also are coming up on the end of our introductory workshops, but then pivoting into our pilot demonstrations. So although we have been talking about additive, coming off of the conversation about those who are additive curious, I really like that statement about, you know, not thinking of the geometry, but more so the function. And so generative design is a design for additive that can really help to take out the perceptions that us as humans would put onto our respective parts that we may be curious to additively manufacture. So we do have these pilot demonstration opportunities across the 6-state ecosystem throughout Nerdic. If you are a defense supply chain company having some criteria that is listed on the previous slide as well as on our website, we really do encourage you to sign up for these pilot demonstrations, so that way you can leverage all of the amazing technology and that technical depth of knowledge from folks like those from Maine and Vermont. So you'll see that it says May 28th for a deadline for this generative design pilot. We will be extending that because we do not yet have a full house of 6 companies that we want to take advantage to pilot design for additive. So that will be extended for another 2 to 4 weeks. So if for those across the Maine and Vermont and beyond New England ecosystem, we please do encourage you to connect. It's really just an amazing free resource that you'll be able to take advantage of to be additive curious. So with that being said, I think we have maybe just one more slide that we'll want to pivot to, and that would be our next webinar, which will be following the Memorial Day weekend. On June 8th, we'll start diving into model-based definition. So that will complete our series when we talk about how do we really create a 3-dimensional blueprint, if you would say, with all of that technical data to really help foster the ease of use for, you know, building a part, whether it's additive or hybridly. So we'll be closing in on the remainder of our workshops, and that would be for on-machine probing, following that MBD, and then we get into our technology demos. So these will be, you know, showcased in real time with real supply chain companies across the Nerdic ecosystem. And we encourage you to visit the Nerdic website, ccat.us/Nerdic, to learn more. And again, I can't say enough for really leaning on the technical expertise of the folks on this webinar today, but as well those who have joined us in the past. So with that, we're right on the top of the 90-minute hour. I really do appreciate your time and attention, especially to those who have contributed this afternoon. There will be a brief survey that will display after you X out of GoToMeeting, so we encourage you to please provide us with your feedback. And again, I'm standing in for Nasir Manin, who really is our Industry 4.0 expert, so please do reach out to Nasir if you have any additional questions. With that, we'll sign off. Have a great day and enjoy the holiday weekend forthcoming. Thank you.
All right.
Yeah.